In this session, we are going to see some new points like atomic number and mass number of the elements. Okay. First, let us go through the atomic number. Each element has been assigned with an atomic number that represents the number of protons present in the nucleus of that element. So, the number of protons in the nucleus of an element determines the identity of the atom. So, based upon the number of protons present in the nucleus of an atom, its atomic number is assigned. So, how many number of protons are there? The same number is given as its atomic number, because for each and every element, the number of protons in the nucleus of its atoms determines its properties, like identity of that atom. Okay, it is denoted with the symbol capital Z. So now we can say atomic number Z is equal to number of protons. It is also equal to number of neutrons if the atom is neutral. If it is normal atom, we know normal atoms are neutral atoms. They contain equal number of protons and electrons. And hence, we can say atomic number is equal to number of protons as well as number of electrons also. Okay, but in case of ions, atomic number cannot be taken as number of electrons. Always get atomic number will be equal to number of protons, because even it is an atom or ion, number of protons won't be changed because they will be existing inside the nucleus, so that number won't be changed. So we can say atomic number is always equal to number of protons, but it is also equal to number of electrons if the atom is in neutral position. Okay, if it is an ion means we know it is formed either by gaining of electrons or by losing of electrons. That's why in case of ions, atomic number is not equal to electrons. Only in case of neutral atoms, atomic number is also equal to number of electrons along with number of protons. Okay. Next, let us see this next one more concept about atoms is mass number. The mass number is the total number of protons and neutrons present in the nucleus of an atom, an element of an element. Okay, total number of protons and neutrons present in the nucleus of an atom is altogether considered as mass number of that element, because we know in an atom the main fundamental particles are electrons, protons, and neutrons. And out of these three, electrons are having negligible mass when compared to the mass of these two, isn't it? So now the mass of the atom is totally because of these protons and neutrons. That's why the number of protons and neutrons is total considered as mass number of an element. Protons and neutrons present in the nucleus of an atom are collectively known as nucleons. So we call these two together as nucleons also, isn't it? So therefore, the mass number is also known as the nucleon number. Nucleons nothing but protons plus neutrons. So the sum of protons and neutrons is equal to nucleon number, which is also called as mass number. So we can represent this mass number with capital A. Okay, uppercase A. Mass number A is equal to number of protons plus number of neutrons. Now, the number of neutrons in an atom is equal to the difference between the mass number and atomic number. So, if you know mass number and atomic number of an element, then we can find out the number of neutrons present in that atom, because atomic number is number of protons. Mass number is equal to sum of the protons and neutrons. Now from these two, if you take the difference between these mass number and atomic number, that gives number of neutrons. So mathematically we can represent like this. Number of neutrons n is equal to mass number A minus atomic number Z. So it is to be noted that all the three quantities, atomic number, number of neutrons, and mass number, are positive integers, because there will be no negative protons or neutrons or electrons, isn't it? There won't be negative number. That's why these three quantities. What are those three? Atomic number, mass number, and even number of neutrons also. These all will be always positive integers. The atomic mass of an element corrected to the nearest whole number is its mass number. Yes, for some atoms, atomic masses may be fractional numbers also. So if these atomic masses are uh, corrected to the nearest whole number, then they will be equal to their mass number. For example, if you see the atomic mass of phosphorus, it is equal to 30.975 atomic mass units, AMUs. This is calculated by comparing with 1 AMU that we have learned already. So how many times it is being heavier than 1 AMU is it taken as its atomic mass. So atomic mass of phosphorus is equal to 30.975 atomic mass units. If it is corrected to nearest whole number, what is the nearest whole number to this 30.975? 31. So the mass number of phosphorus will be equal to 31. It means it has 31 nucleons in its nucleus. Total number of protons and neutrons for the phosphorus will be 31. Next, let us see how to represent an atom. Representation of an atom, let us see here. The most accepted way to denote the atom of an element X is ZXA, where X represents the symbol of that element. X representing the symbol of that element, and Z represents atomic number of that element, and superscript A represents mass number of that element. Okay, first we write the symbol of that element in upper cases. At the front bottom or at the what we call this subscript position, we represent its atomic number. At the right side top, that we call superscript position, there we represent its mass number. So in this way, the symbol or an element or atom is represented. For example, the atomic number of carbon is 6, means its Z value is 6, and its mass number is 12, means atomic atom mass number A is 12. The atomic and mass numbers of carbon can be represented as, we know the symbol of carbon as C. So first symbol of element is written at front bottom, that we say subscript position. Its atomic number 6 is represented, and the right top in the superscript position beside the symbol, its mass number 12 is represented. Now it is a symbolic representation of carbon along with its mass number and atomic number. Okay. Now based upon these fundamental particles, based upon the electrons, protons and neutrons, based upon the relation between these, let us see some relations between the atoms. One among them is isotopes. Isotopes means the atoms of an element which are having same atomic number but different mass numbers are called isotopes. Isotopes means the atoms of an element, atoms of same element which are having same atomic number but different mass numbers are called isotopes. For example, if you see hydrogen, it has three isotopes, namely protium, deuterium, and tritium. If you observe these three, all they are having same atomic number, because at the left bottom in the subscript position we represent atomic number. See, these three are having same atomic number 1, and if you observe their mass numbers, they are different. Protium is having a mass number 1, deuterium is having mass number 2, and tritium is having mass number 3. This is because of the difference in the number of neutrons existing in these. So as there is difference in the number of neutrons, their mass numbers are being different. So it has only one proton, no neutrons. That's why its mass number is 1. And if you observe this, it has one proton and one neutron, deuterium. So its mass number is 2. In similar way, tritium has one proton, two neutrons. So its mass number is 3. So what do we observe here? These three are having same atomic number, but at different mass numbers. So in this way, the atoms of an element which are having same atomic number but different mass numbers are called as isotopes. Okay. Let us see some more examples. If we take carbon, carbon also has three isotopes, namely carbon 12, carbon 13, and carbon 14. The most predominant isotopism means mostly existing isotope is carbon 12. The remaining two, they are carbon 13 and carbon 14 are existing in the rare quantity. Okay, these three are the isotopes of carbon. In the same way for hydrogen also, protium, deuterium and tritium we told. Out of those three, most predominant one is protium. Hydrogen with one proton, one electron without neutrons is mostly existing hydrogen. And the remaining two, which we call as deuterium and tritium, those two are existing in the rare quantity. In the same way, chlorine has two isotopes. That is, chlorine occurs in nature in two isotopic forms with masses 35 units and 37 units in the ratio 3 is to 1. So, chlorine also having two isotopes, means the atoms with the same atomic numbers but different mass numbers. So, one isotope is having mass number 35 units, whereas other isotope is having mass number 37. So, these two are existing in the nature in the ratio 3 is to 1. So the chlorine with mass number 35 is existing around 75% in the nature. Its abundance is 75%. It is mentioned here. And the chlorine with mass number 37 is existing around 25% in the nature. That we call as abundance. So its abundance is 25%. Now we may get one doubt. Obviously, the question arises like this: what should we take as a mass of chlorine atom? We are telling mass number 2, different mass numbers we are expressing. Then what should be its atomic weight or atomic mass? What should we take? The mass of chlorine atom. Now let us try to find it out. The mass of an atom for any neutral element is taken as the average mass of all the naturally occurring isotopes of that element. So if an element is existing with more than one kind of isotopes with considerable amounts, then mass number or atomic mass of that element is taken as the average of masses of the all the naturally occurring isotopes of that element. Now let us try to see if an atom has no isotopes, then the mass of its atom would be the same as the sum of the protons and neutrons. If an atom is having no isotopes, only one kind of atoms if it is having, then directly the number of nucleons is taken as its mass number or atomic mass also. Okay, if it is having more than one kind of isotopes, then we will calculate the atomic mass or mass of that atom by taking the average mass of all the naturally occurring isotopes of that element. But if an element occurs in isotopic forms, then we have to know the percentage of each isotopic form, and then the average mass is calculated. So we told just now, if an element, if it is existing with more than one kind of isotopes, and if we know the abundance or the percentage abundance of those isotopes in the nature, then we can calculate the average atomic mass by using the formula. Average atomic mass or atomic weight of an element is equal to mass number of first isotope into its abundance percentage plus mass number of second isotope into its percentage abundance divided by total percentage of abundance. This gives the average atomic mass or atomic weight of that element. Now let us consider chlorine itself. We told chlorine is having two two types of isotopes. Chlorine with mass number 35, which is existing with abundance 75% in the nature. And one more isotope of chlorine is that is with mass number 37. Its percentage abundance in the nature is 25%. So now we know the mass numbers of two types of isotopes of chlorine and their percentage abundances. Now the average atomic mass of chlorine can be calculated by substituting these all values in the above formula. What is that? Mass number of first isotope. Suppose if we consider this is a mass number of first isotope into its abundance 75 plus mass number of second isotope 37 into its abundance 25. Now total abundance means 100. So if you substitute these all values, see here we get it as 35.5. This is why we write the atomic mass or atomic weight of chlorine as 35.5. You might have seen in the tabular columns representing atomic weights of elements. For chlorine it will be shown 35.5. Why? Because it is existing with two different isotopes with a considerable amount of abundance. Okay, that is why chlorine is getting its atomic weight as 35.5. Did you understand how we got this 35.5 for chlorine? By calculating with this formula. You may get one more doubt also. Even hydrogen is also having three isotopes, but its atomic weight is considered as only one. It is not any fractional number. Why? Because for hydrogen, the abundance of remaining two isotopes is not considerable amount. They are existing in the very rare quantity. That is why directly the atomic weight mass number of the isotope which is existing in the large quantity is taken directly as its atomic weight 1. Okay, if there are more than one isotopes the considerable amount of abundance, then we have to calculate its atomic weight by taking this formula. Okay, next let us see one more relation between the atoms based upon the fundamental particles is isobars. The atoms which are having same mass number but different atomic numbers are called isobars. For example, if you see argon and calcium, these two come under set of isobars, means they have same mass numbers but different atomic numbers. Let us see here their fundamental particles quantity. Their atomic masses are 40 for each, whereas atomic numbers are 18 and 20 for each, argon and calcium. This is due to the difference in their number of neutrons. Argon has normally 22 neutrons, whereas calcium is having 20 neutrons. So their atomic numbers are 18 and 20. So the number of protons is here 18 and here it is 20. But the sum of the protons and neutrons is being 40 for each. So the number of protons and neutrons we also call as nucleons. So these two are having same number of nucleons. That's why they are called isobars. Their mass numbers are being same. Atoms the same mass number but different atomic numbers are called isobars. We can say argon and calcium are isobars because they have same mass numbers even though they belong to same different elements. Means they have different atomic numbers. Okay. Next, one more relation is isotones. Atoms of different elements having same number of neutrons but different atomic numbers and mass numbers are called as isotones. So isotones means the atoms with the same number of neutrons but they'll be having different atomic numbers and mass numbers. Only the relation will be between those two atoms will be number of neutrons. If both are having same number of neutrons, then they are called isotones. Let us see an example. If we say silicon and phosphorus, if you observe for both, now atomic number is different. Phosphorus atomic number is 15, whereas for silicon it is 14. And mass number of silicon is 30, and mass number of phosphorus is 31. These two are also different. So atomic numbers and mass numbers Both are different. But if you calculate the number of neutrons of these atoms, how do we calculate number of neutrons? We know number of neutrons is equal to mass number minus atomic number. For this, if you for silicon, if we calculate mass number 30 minus number of atomic number 14, so we get 16 neutrons for silicon. If we observe for phosphorus, mass number 31 minus atomic number 15 gives number of neutrons, that is also equal to 16. So this silicon and phosphorus both are having same number of neutrons but at different atomic numbers and mass numbers. Hence these two are called isotones. Atoms with the same number of neutrons but different atomic numbers and mass numbers are called isotones. Okay, these are some relations between the atoms based upon the number of fundamental particles existing in them. Thank you for watching our video. Please subscribe our YouTube channel AIMS Today and visit our website aimstoday.in for latest updates on recorded videos.